Hello student, today we are going to start our question related to the Biot law. In the last class we did, we'll go for the small recap. Basically in the Biot law we did that magnetic field at point P due to this element is what? This is delta B, it is equivalent to mu naught 4 pi I dl sine theta upon r square. See, we'll have a simple numerical based on this. That is, they will give that the current carrying element is, let us suppose, 1 centimeter. This is delta L. They will say this is the point P where we have to calculate. Let us suppose it makes angle theta is, let us suppose it is 45 degree. Then it's a distance of this small element from here is 2 meters suppose, and current flowing through this element is 3 ampere. So what will be the strength of the magnetic field at point P? So what we will do is that we'll apply this formula. This is mu naught upon 4 pi is basically going to be 10 to the power minus 7. I we have as 3 ampere. Element is what? 1 centimeter means 1 into 10 to the power minus 2. Sine theta, we have theta is 45 degree, it is going to be 1 by root 2, and this is what? Distance. Distance is 2, so it becomes 2 square, and this will be the strength of magnetic field in Tesla. Whatever the result, we'll sort it out. Now we have done the application of Biot's law, that what is the strength of magnetic field at the center of circular current carrying conductor. What we got the result as? That was mu naught I upon 2r into n. In this case, when we have to determine the strength of magnetic field at the center of circular current conductor, what we will have is that they will only give us the amount of the current. Let us suppose it gives 1 ampere and distance is what? 2 centimeters. Suppose what is that? Radius of the circle, and they might give that number of turns is 100. In that case, what we'll do? This is what? Mu naught is going to be what? 4 pi into 10 to the power minus 7. 4 pi into 10 to the power minus 7. Current is what? 5 ampere. This is 2. Radius of the circle is what? 2 centimeter. 2 into 10 to the power minus 2. And we are given number of turns as 100. We'll multiply it by 100 to get the strength of magnetic field. This will be in Tesla. So, and the direction of magnetic field will be determined by using Fleming's right hand rule. And now what we'll do is that all the direction, most of the direction determined by right hand thumb rule over here. In the case of, what we did was that magnetic field due to straight current carrying conductor. What we had derived in the last class, that the strength of the magnetic field due to this element at a distance r is basically what? Mu naught upon 4 pi I, this is the, let us suppose this is the distance a, into sine phi 1 plus sine phi 2. This was the strength of magnetic field due to straight conductor at point P. See, the question based on this will be like, they will ask you to find the strength of the magnetic field at the center of a square. This is a square and it has current I. Then what is the magnetic field at the center of the square? See, applying this formula, let us suppose what we have studied over here. This is distance A, this is phi 1, this is phi 2. So over here also what we have? B will be equivalent to what? mu naught upon 4 pi I, this distance is going to be what? A by 2. And since it is a square, it will make this angle phi 1 and phi 2 both are going to be what? 45 degree. So what will happen over here? We'll have, this is A by 2. This is what? Sine 45 degree plus sine 45 degree. And again applying right hand thumb rule, we are getting that all are contributing the magnetic field in the downward direction. So what will happen? The net magnetic field will be equivalent to what? 4 times the strength of magnetic field due to one side. This is 4 pi, this is I, A by 2, this is twice 1 by root 2. This is going to, what we have done? We have multiplied by 4 to get the net strength of the magnetic field due to square which has side A, and the current carrying, the strength of current is I. Similarly, like we can go for magnetic field at the center of a triangle, equilateral triangle. Suppose it is all the sides are same and the strength of magnetic field is what? I. So our target is to find strength of magnetic field at the center of the triangle, equilateral triangle to be precise. See what will happen over here? We have to go for the strength, the distance part. We know that it is equilateral, so when we draw a perpendicular over here, it will be what? A by 2. And we know that in the case of equilateral triangle, angle is 60 degree and half of it is going to be 30 degree. So this is 30, this is perpendicular distance. So this is going to be 90. So this comes out to be what? 60. Again applying this formula over here, what we get? Mu naught upon 4 pi, this is I. We need to get this distance. How to get that? We'll go for like tan theta. Tan theta means tan 30 degree. In that case, what we'll do? See, let us suppose we have a rectangle. This is side 2A. This is side 2B. Current is I again. We'll apply the same formula over here also. See, what we'll see that? Suppose we draw it like this. So over here, what do we see? This is angle phi 1, this is phi 1, vertically opposite angle, this is phi 1, phi 1. So what will happen? Over here, we'll first calculate magnetic field to this element. And that will be what? Mu naught upon 4 pi I upon, this distance is how much? This is 2b, it is going to be b. And over here, what we'll have? We'll have sine phi 1 plus sine phi 1. What will be the sine phi 1 be? Sine phi 1 will be equivalent to C. This is A, and we know this is the total is to B, this is going to be B. This is going to be what? A square plus B square. Sine phi is how much? This is mu naught upon 4 pi I upon B. Sine phi is what? This is going to be perpendicular upon hypotenuse. Again, we have the same sine phi 1. It is again going to be this one. And what we see that this and this are symmetrical. Both have same contribution. What we'll do is that this element will be twice. Again, we'll go for this element part. Contribution of magnetic field due to this element will be how much? This is B1, let us suppose. B2 will be how much? This is, let us suppose this makes angle phi 2 over here. This is phi 2. See what we'll see that this is mu naught upon 4 pi I. This distance is how much? It is A into, this is mu naught upon 4 pi I upon A. This is what? Sine phi 2 plus sine phi 2. And we see that contribution due to this element and this element are going to be same. What we can do is that we can twice it out. So what we have, this is mu naught upon 4 pi, this is I upon A, this is sine phi 2 is how much? This is perpendicular, this is B, this is root over A square plus B square, this is also B upon root over A square plus B square, and this is twice. So the net magnetic field due to all these elements will be equivalent to what? B net will be equivalent to B1 plus B2. We'll add this and this to get the total strength of the magnetic field at the center of a rectangular element which has side 2A and 2B. Now what we can do is that, what is the strength of the magnetic field due to current on the axis of circular current carrying conductor? We had done the derivation part Now, what is the strength of the magnetic field due to? See over here what we have, this is phi, this is phi, this is phi, this is phi. Now we'll see that we had derived over there was like, this is, let us suppose this is a, this is x, this is going to be a square plus x square. We got the net result was what? That was mu naught upon 4 pi into 2m upon a square plus x square to the power 3 by 2. And what was capital M? That was, capital M is basically magnetic moment. Magnetic movement, and that is what? N into I into A. This is the area. Area of circle is what? Pi a square. And this is what? Magnetic movement. So, if any question is given to us, we can have this direct formula and we can place. Basically, we have to remember that A is basically the radius of the circle over here. Radius of circle, and then x is distance of this point. Distance of the point where we have to calculate the magnetic field from the center of the circle. So basically you need to remember that this case is what? Magnetic field at the axis of circular current carrying conductor. This is what? Magnetic field at the axis of circular current carrying conductor. We have, like in the CBSE board examination, we have like simple question based on it. What we can do is that we need to know the derivation part as well as how to manipulate the question. That's all for today. We'll meet in the next class.